Hello everyone, my name is Kongdi from Tsinghua University. Today I will introduce our CVPR 2026 paper, GaussianPile, a unified sparse Gaussian splatting framework for slice-based volumetric reconstruction. The key idea is simple. We adapt 3D Gaussian splatting from surface rendering to internal volumetric imaging by explicitly modeling the finite slice thickness of real imaging systems. Slice-based volumetric imaging is widely used in biomedical and scientific applications, including 3D ultrasound, light-shade microscope, and structured illumination microscope. However, these datasets are often stored as dense voxel grids whose memory grows cubically with resolution. This makes storage, transmission, and interactive exploration increasingly expensive. Existing codecs are efficient but may lose structural details. INR-based methods are compact but usually slow to optimize and render. 3D Gaussian splatting is attractive because it is explicit, differentiable, compact, and fast. But the original 3D GS was designed for surface appearance, not for internal volumetric reconstruction. A direct adaptation of 3D GS to sliced images leads to a subtle but serious problem. Standard 3D GS can fit 2D rendered slices reasonably well, but the underlying 3D structure may become inconsistent. This is because surface rendering relies on view-dependent color, opacity blending, and occlusion. In contrast, slice-based imaging measures internal density or intensity, where signals are accumulated inside a finite slice thickness. Therefore, a plausible 2D projection does not guarantee a faithful 3D volume. Our key observation is that slice-based imaging is neither all-in-focus rendering nor an ideal zero-thickness slicing process. In real systems, each slice has a finite Ansel sensitivity. Structures near the focal plane contribute strongly, while the out-of-focus structures are attenuated. This finite thickness model is essential for ultrasound and the microscope, where each pixel receives contributions from a small but non-zero depth range. GaussianPile is designed exactly for this intermediate regime. GaussianPile represents the volume as a set of anisotropic 3D Gaussian primitives. Given our target slice, we first scan the Gaussian set at the corresponding depth. Then we introduce a sensitivity map to model the finite focal zone. This gives us a focus Gaussian, a standard 3D Gaussian modulated by the imaging system's Ansel response. Next, we perform Ansel reparameterization and opacity modulation so that primitives close to the slice contribute more, and distant primitives naturally fade out. Finally, instead of alpha blending for surfaces, we use additive rasterization to form slice intensities. In this way, the same set of Gaussians must explain multiple slices consistently, which enforces faithful internal 3D structure. GaussianPile is optimized with differentiable CUDA restoration. During training, we randomly sample virtual slices, render them through the focus-aware forward model, and optimize Gaussian positions, scales, rotations, and intensities. We also designed a compact encoding scheme. Gaussian parameters are spatially sorted, quantized, delta encoded, and entropy compressed. This preserves the rendering efficiency of Gaussian primitives while turning the reconstructed volume into a compact and interactive representation. We evaluate GaussianPile on automated 3D breath ultrasound, light-shade microscope, and several cellular microscope datasets. Compared with HEVC INR-based methods and the slice-adapted 3D GS, GaussianPile better preserves breast tissue structures, tumor boundaries, and fine intracellular details. Quantitatively, it achieves strong 2D slice fidelity and, more importantly, better 3D volumetric fidelity. In practice, GaussianPile produces high-quality results in as few as 3 minutes, runs up to 11 times faster than nerve-based approaches, and achieves consistent 16 times compression over voxel grids, with some cases reaching 26 times compression. We further test GaussianPile on highly anisotropic electron microscope data, near billion voxel volumes, and industrial MIR OCT data. These results show that the method is not limited to a single biomedical modality. It generalized to diverse slice-based volumetric data while preserving task-relevant internal structures. To summarize, GaussianPile introduced a physics-aware Gaussian representation for slice-based volumetric reconstruction. It combines the compactness and the speed of Gaussian primitives with a thickness imaging model, enabling high-fidelity reconstruction, compression, and interactive visualization of internal 3D structures. And that's all. Thank you for watching.